Hello and welcome to this MCMA webinar, Sensing a Revolution. Magnetic sensing technologies are changing how you use rotary encoders. My name is Joanna Keel and I'm the Manager of Marketing and Membership for the MCMA. This webinar will be recorded and a link will be sent to you within the next 24 hours. If you have any questions, please submit them in the questions panel of your webinar screen and we will answer all questions at the end of the presentation. Now, I'd like to introduce our webinar presenter today, Jarrod Orszulak. Jarrod is a Product and Business Development Manager at Posital-Fraba. He focuses on using Posital's mass customization to find unique yet economical solutions for customers' position and motion sensing challenges. Previously, he worked as a research engineer at Massachusetts Institute of Technology Age Lab, investigating how technology can be applied to understand how individuals make decisions on health, finance, and driving. He holds an MS in electrical engineering and a BS in biomedical engineering from the University of Rochester. This webinar is sponsored by the following companies. Electromate. Electromate is a co-sponsor of today's webinar and Posital-Fraba's distributor. Electromate's core purpose is to help manufacturers build better machines using differentiated automation technology. They specialize in robotic and mechatronic solutions for industrial automation marketplace. Respected by customers as a premier source for high-performance automation and motion control components and systems, Electromate specializes in servo and stepper motors and drives, motion and automation controllers, positioning systems and actuators, feedback devices, gearing products, operator displays, and all supported via extensive product selection, just-in-time inventory, dedicated to customer service and technical engineering support. Fraba is the North American sister company of the Netherlands based on Fraba's BV group of enterprises focused on providing advanced products for position sensing and motion control in many sectors and applications. Business units within the Fraba group include Posital, position sensors, and Vitector, safety assurance equipment. Thank you again to all of our sponsors, and now I'd like to hand it over to Jarrod.
Thank you for that, Joanna, and thank you to everybody for calling in this morning to learn a little more about encoders. This is a great opportunity to speak with you all, and I'm very excited and grateful to be here. Again, this is myself, Jarrod Orszulak. I'm a product manager with the Posital brand of Fraba Incorporated. Here's my email, so I look forward to your questions at the end of this presentation, but also afterwards. Goal of this is to not necessarily cover all the bases, but rather to start some interesting conversations and inform everyone a little more about the current market. Quickly also, I'd like to acknowledge Electromate for their help in making this possible as well. So getting started, want to give everybody a quick little history lesson. So we're going to start by going over, where did encoders get developed? How did we get to where we are today? Specifically talking about the status of optical and magnetic encoders in the marketplace. Kit solutions that are becoming available now, and how do you choose an encoder? I think a lot of the people on this call are probably on the application side of thing, and to some degree they're not as interested in what's going on in the black box, but rather how do they get the right unit for their application. And then last, we'll go ahead and actually look at some of these applications and opportunities that can be addressed with some of the different sensing solutions. So in the 1950s, optical encoders were first developed to assist in space flight. Engineers needed higher resolution, longer lifetime, and they did it by relying on an optical code disk. Before then, your encoder was probably some sort of potentiometer, just like the ones that we used in high school physics lab, if you will. So the optical encoder really developed as a, certainly a higher resolution device compared to that noisy contact mechanism that you would have in a simple potentiometer. These first encoders were incremental encoders. And an incremental encoder has an output that's processed by some external electronics. So this is going to be your first comparison to that potentiometer, where it's all internally, just a mechanism. The encoder outputs pulses as the shaft is turned. And the encoder must be homed, otherwise it only knows its relative position. So if you will, an incremental encoder is similar to a stopwatch. You know that some amount of time has passed, or you know that some amount of distance has passed. Whereas an absolute encoder, which we'll get to, is kind of like the clock on the wall. You can look at it and know the exact time. Incremental encoders are commonly used in a speed application. So as the pulses come out of the encoder, you can divide it by some unit of time, and you can know the rate at which a shaft is turning. And then most incremental encoders have an A and a B pulse, so that you can determine which way you're counting, whether you're increasing or decreasing with the counts. Fast forward to the 1960s, and you'll see the introduction of LEDs, which would provide a stable lighting environment for the units. And at this point, encoders start to move into new applications. So we're getting out of that space and defense, and we're starting to trickle our way down to other applications. So we're becoming a little more mainstream here. In the 1970s, you'll start to see absolute optical encoders. So as I referenced earlier, the absolute encoder is going to have a unique position on the code disk. So here on the left, you can kind of see the incremental encoder with the pulses, and on the right, you have your absolute encoder with the pulses. And what you would have is the opto, I would be looking at the pattern of light and dark. Absolute encoder, you now start to see the use of multi-turn encoders, which not only could give you a position 0 to 360 degrees, but could also tell you how many revolutions the encoder had been through. Advantage of this is now you have further tracking for your position data. The other advantage to the absolute encoder is it continues to work even if the power goes out. So you can imagine this this code disk, whether it has power or not, when you power it up, there's a unique pattern of light and dark spots there, and the encoder would know where it is. In the 1980s, we start to see Fieldbus networks such as CAN-Open get developed. The new complexity is supported by encoders. You have your absolute position, but you also begin to see other parameters that weren't possible with an absolute encoder before, such as velocity. The other advantage to Fieldbus is you can provide status information. So you have simplified wiring due to the network topology. Combine it with the status information, now you have diagnostics, controls as being easier, and you can create much more complex networks. As a result, you now see encoders moving again to some new applications such as mobile machinery and material handling being two of the ones that have really taken advantage of Fieldbus and largely use it still to this day. In the 2000s, we start seeing the Ethernet interfaces develop. We've all talked about Internet of Things, probably till we've been blue in the face. Encoders are no different. They're here for that party. Whether you're using an EtherCAT, PowerLink, Ethernet IP, Profinet, et cetera, the list goes on. There's probably an encoder with that interface ready to go. With some of them, you'll also see the real-time sensing. Each kind of has its own advantage as far as a sensing network. And to some degree, you'll see the encoders are tailored to that. Kind of happening in parallel at the opposite extreme of the high-end Ethernet sensors, you started to see magnetic encoders become more mainstream and hit the market. These were relying on a Hall effect sensor. I won't go into the details and a lot of it itty-bitty specs, but in short, the Hall effect sensor, you have a magnet rotating near a sensor, and as that magnetic field changes, you can determine the position. So while the 0 to 360 single turn resolution was being redefined on how we were measuring it, engineers were also looking at, well, how should we do the multi-turn that goes with it? So some options include the Weigand effect, which we'll talk about in a little more detail later, as well as batteries and gearing. Gearing being how things have been done, for the decades before. So the advantage to the magnetic encoders is that they're compact, they're low cost, and they're robust. The disadvantages is you have a high latency time, so they really weren't good for high-speed applications. They're susceptible to EMC, being a magnetic sensor, temperature drift, and then also limited resolution and accuracy compared to their optical counterparts. And what this did was it had some limitations on the actual use of them. So the biggest thing being the magnetic encoders were largely being used as absolute sensors because of that high latency time. They really weren't appropriate as an incremental encoder where it would be expected that you could have a accurate position at higher revolutions and speeds. So one of the big breakthroughs that came with the introduction of the magnetic encoders was Weigand Technology. This was a technology that dates back to John Weigand before. Guy was actually trying to develop a different guitar string and somehow stumbled across this Weigand effect, which is an energy harvesting technology. And the reason why that this technology was necessary was the traditional gear sets didn't complement the magnetic encoder's strengths. So magnetic encoders, they're small, they're robust, they're low cost. Well, a complex gearing system isn't any of those things. Anybody who's ever seen the inside of a clock or a watch knows they're intricate. They're do require some space, no matter how small and complex you make it, and they're not exactly cheap. Anybody who's bought a nice watch knows. Batteries are bulky, they have a short lifetime, they're difficult to dispose of, and even more recently we're having more and more regulations where they're trying to eliminate batteries. So to go on a quick aside, we all heard about battery problems with some of the new Boeing jets and stuff, and the word is right now that they're trying to eliminate all the batteries where possible in the sensing technologies on airplanes. So the Weigand technology offers a reliable counting even with no power. So what the Weigand technology relies on is it's a self-powered counter, and what makes it so neat is that it can give you energy and position information from 0 RPMs essentially. So many of us are probably familiar with how a dyno works. You can imagine a headlight on your bicycle, and the faster you pedal that bicycle, the brighter that headlight gets. So you're getting variable power with your RPMs. And what makes the Weigand technology so cool is it's going to give you a consistent power regardless. And again, I don't want to go into too much detail here, but what we're relying on is that piece of Weigand wire, as the magnetic field changes, it develops a potential energy, and when it crosses a threshold, it releases it as a burst. And in short, what that burst does is it's a large enough energy pulse that the encoder can realize, one, that it made a rotation, and then secondly, whether that rotation was made, clockwise or counterclockwise, so increasing or decreasing. So if you look at the bottom of the graph on the right-hand side, you can see that regardless of rotational speed, the energy pulse that's generated is consistent. So unlike the headlight of our bicycle that depended on RPMs, this is going to give you a nice consistent pulse. So what makes this so great is you can imagine having a machine, it's not in use, it gets moved. 10 years later, you move it back, you go to plug it in, it's going to pick up, it's going to know right where it is. So how do you take all this information, all these ideas, and put them together into a new package? So on the encoder on the left here, this is a traditional optical multi-turn encoder. The one on the right would be a traditional magnetic encoder. So you've been listening to me talk about, what costs more, costs less, etc. I think this picture really does a better job at explaining it than I can. So when you look at the optical encoder on the left, you can see as you work your way down, you have the shaft and the flange. You have then a intricate code disk, some sort of eye to read it all. Then you have all this gearing, some sort of communication interface, and then you got to put it all in a housing. Whereas with the magnetic encoder, you just have a magnet mounted onto the shaft. You have the board with everything on it on one PCB, and then you combine it with the housing. So at this point, ignore everything I said so far, and you can ask yourself, if you were to buy one of these, which one would be less expensive? Well, probably the magnetic, the one with less components. Which one's going to be more robust to shock and vibration? Well, probably the one on the right, the magnetic, because it has less components, less things to break. Ignoring everything about the gears and the optical code disk, which are even other reasons that make the optical encoders even more susceptible to damage. So in short, if we go back and look at history, here's some encoders over the years. You can see on where we're progressing. So at this point, what I kind of wanted to do is round the corner and talk about the new technologies that we have. And the most important thing to do before we talk about the new technologies is to ignore everything that we just spent the last 15 minutes talking about. Because all those gotcha downfalls of the magnetic encoders have been addressed. And we're going to talk about the new magnetic technology and how it can be used in a lot of different ways that previous components weren't able to. So if you're just tuning in now, your time is absolutely perfect. So the biggest thing to realize is the new magnetic technologies are possible because of advancements in microprocessor technology. We can have 32-bit microprocessors, all the electronics down on one 35mm board is really a huge advancement in computational power. The latency time, which has always been one of the biggest downfalls of magnetic encoders, is now on par with the optical encoders. We have much better accuracy, improved from being about 0.36 degrees to now 0.09, and then also we can do 16-bit resolution now with the magnetic platform. And while we've been doing this, we've been able to maintain the robustness of the magnetic encoders as well as their compact size. So we haven't had to give back much to gain it. And what this does is this sets up this concept called mass customization. And what makes mass customization so powerful is that things are based on software, not hardware. So as a result, we can offer a real broad range of products to systems integrators, OEMs, and customers alike. So no longer do you have to be a tier 1 customer to get what you want. Rather, you can get the right product quickly at a good price for your application. And what this does is it means we have a larger standard selection. Customization is easier because a lot of the customization is software driven. Also, software changes can even be made in the field. And what this really does is it makes it economical. So like I said just a moment ago, everybody gets to benefit from this. This isn't something that's isolated only to the big customers who have a lot of, who are buying tens of thousands of encoders a year so they get what they want. Getting back to the technical details, we had talked about latency. This is a really powerful graph here. So what this plot shows is, we have three encoders: the blue, which is our traditional optical encoder; the red, which is the new magnetic encoder; and the green, which would be a traditional magnetic encoder, if you will. And all three encoders are sitting at rest, and then at 1,000 milliseconds, they are all set to 6,000 RPMs at a rate of 10,000 radians per second squared is the acceleration. Oh, excuse me. Sorry about that. Excuse me 1 second. Lost my slideshow. I'm sorry. Okay, great. So I apologize for that. So looking at this plot, the three encoders, in short, are all undergoing acceleration up to 6,000 RPMs at 1,000 milliseconds. And what we're looking at is the position error, so the absolute position of the encoder. And what you can see is even once after a couple seconds, when the the RPMs are a steady 6,000 RPMs. The old magnetic technology, the green one in the plot, has a consistent position error of about 40 degrees, which is quite a bit, whereas the optical and the new magnetic technology both have something much, much less than 1 degree, essentially hardly budge off that original line. And I think this really shows two things. One is the advances in the magnetic technology, but it also shows that the magnetic technology really is appropriate for use in dynamic situations such as motor feedback. What this also does is this sets up kit solutions. And the idea behind a kit solution is that rather than having a traditional magnetic encoder, you can go and provide a customer with simply a magnet and a PCB to sense the motion. And this has become possible because advances in the microprocessing allow for an off-centric mounting and also increase accuracy and resolution from what we previously had. And why a customer might want to do this, there's a few different reasons. One is space is often an issue. The other would be price. So once you get beyond the PCB itself, the most expensive part of an encoder is typically the flange. You need to have some high-end ball bearings and different things there. So it's very important to have that. The other thing about a kit solution is you can offer a lot of different options to the customer. So now it could be an absolute single-turn encoder, it could be an absolute multi-turn encoder. All these are on one single PCB. It could also just be a multi-turn counter. You can imagine an application where somebody has either only needs to count the number of turns or already has a single turn counting mechanism, whether it's an encoder or something else that works well, but maybe they are using a battery backup or gears and they want to get rid of it. It's very compact, robust, because we're still keeping all those advantages that we previously had with the magnetic sensors. The other thing is because we're using an encoder as compared to a resolver or a different interface, we can now introduce the digital communication interfaces, whether it's SSI or BIS or something else, which means you have a signal coming right from your encoder going right into your drive or your system for immediate processing. You don't have the expense of having analog to digital converter, for example. A lot of advancement has also been made in shielding technologies. Part of the problem with the kit solutions was always, how do you shield that magnetic sensor from EMC or from large fields due to breaks in a motor or other interference. And then last, this all largely revolves around certainly low cost, whether it's a large OEM or even a smaller drives manufacturer potentially who's selling hundreds of drives a year and wants to figure out, well, how can I get a $30, $40 encoder onto a $500 drive? So whether you're in the market for a kit encoder, an optical encoder, a magnetic encoder, you can kind of work through your options all the same way. Best way that I like to do it is from the outside, work your way in. So ask yourself, well, how am I going to connect this? How am I going to couple this to my environment? So that's being your shaft and your flange. Next is, what type of resolution and accuracy do you need? Our experience is people often think they need more resolution and accuracy than they really do need. I think that's the simple reason is people often forget about things like backlash and whatever slop is in their total system. So it's one of those things that we ask people to be realistic with themselves, but we have a lot of different options, and you'll see that most of our competitors, the same is also true. Next being, do you need a single turn or a multi-turn encoder? What are you interested in? Are you interested in the position, or do you need to count the number of turns to know where you're located, how far away something's from home, or potentially even maintenance issues? Next, how are you going to get those signals out? What's your communication protocol? Is a simple incremental giving you pulses all you need because maybe you're just looking for a velocity? Or are you going to take this into an Ethernet network that's going to be used with diagnostics to monitor things? Housing material. What type of environment is this going to be in? Is this something that's just IP54 rated? It's going to be in a shop with a consistent temperature and no washdown? Or is this something that's going to be mounted on a solar panel outside for 2 decades and you're going to need to be able to withstand the sand of the desert and the hot and cold air, etc.? And then finally, how do you want to wire this in? Do you want connectors? Do you want a cable coming out? Do you want a ribbon cable with a custom JST connector? And if you work through all these, you probably get a pretty good sense of what you're looking for. And when you do talk with somebody about encoders or an application, it'll be pretty easy to find the right product. At this point, I just want to take a couple minutes, shift gears, and talk about some of the different applications that are now possible. Food and beverage is one that we think there's a lot of potential for room for growth just because the magnetic encoders have not only a lower cost, but especially when it comes to the high IP ratings, you can see a real significant improvement in the cost. And it just comes down to the fact that they're easier to seal. A device that's more compact is going to have less area that water and humidity, chemicals can get in. You can find these sensors with a V4A 316L stainless steel for the food and beverage industry. You also see that they're easy to install. Lots of different communication options make retrofitting old applications easy. Some of the units can be programmed by the end customer before they put them in. So you can imagine a food plant that over the year uses lots of different machines with lots of different types of encoders and interfaces. So you can keep a handful of products on the shelf and then program them as you need them. Keeping lead times down, keeping stock levels down. You'll also see hazardous environment ratings on these sensors, whether it's UL, ATEX, IEC, EX. So it may not just be in a bottling facility, but you may see this in a grain silo where there's potential of spark and fire. Off-highway, I mentioned this a little earlier with regards to the reference looking at the Fieldbus. these are really robust sensors are what they're looking for. So the magnetic sensors are very appealing, as are the kit solutions. The eliminating glass code disk and gearing, and then again your high temperature wash down when the trucks come in at the end of the day, washing them down, getting the mud off. We've had a lot of interest from the industry as far as OEM applications go, and a lot of this has to do with customization. So traditionally, the big players and off-highway were doing their own sensor development, their own drives development. And this was done for a variety of reasons. A lot of it was so they could get the exact product that they wanted. It could be the size and the form factor. And a lot of it also had to do with availability, because they were the ones controlling it. They were the ones building it, so they always knew they could get it. And the mass customization of the magnetic sensors really addresses a lot of these issues, because most of the customization is software based, so the products are being made out of the raw materials that are on the shelf already. So it addresses a lot of the concerns of large OEMs with regards to lead times. We're also looking at products with a much lower cost, because we can modify standard products, whereas they were building things from scratch. A lot of times it wasn't their area of expertise. So what we've seen is this nice synergy between the mass customization and then also the recent recession causing some of the large players to reduce the staff and groups who are developing the sensors in-house, and rather taking advantage of the sensors that are available from outside. Material handling is an area we've seen a lot of growth. This kind of falls under two categories, if you will. You see a lot of incremental encoders, for example, in the material handling industry and packaging. There's some absolute encoders there as well. This is really where one of the spots where the programmable encoders can shine. Because the customer can, in a new application, can fine-tune the output of the encoder during installation. At the same time, you could have a lot of encoders on an application, and you can reduce your stocking requirements a lot by having a couple of the mechanical models that you need and then putting them in quickly. We also see a lot of easy wiring. So you'll see Fieldbus and even some Ethernet now starting to enter the material handling industry. This is where we group the AGV groups of products into. Really important because you have the diagnostics, you also have the monitoring ability that the Fieldbus and Ethernet encoders bring with it. So there's a lot of growth here from both sides. Last but not least, this is the MCMA, so I want to be complete talking about motors and drives in a little more detail. And the big thing here, this is really, we think, a spot that is prime for the kit solutions because they're compact. Recent developments in shielding addresses a lot of the EMC issues, and then the options that you're giving people. So the single turn, multi-turn, absolute or incremental, different digital interfaces can be really integrated right in. The OEMs will be able to do their own calibration, setting it up with these units. This is a really exciting time because it's so flexible that it really works well to complement the drives that are there. So, in summary, optical encoders are a proven technology, but they certainly have their limitations. There's many manufacturers of them. I don't think they'll disappear too soon. The new generation of magnetic encoders has really head-on addressed the shortcomings of the earlier magnetic encoders. You can really see magnetic encoders as, I would say, a solution in 95% of the sensing issues that you had before. And most exciting is the compact, economical kit solutions are really opening new doors. With that being said, I'd like to thank you all for listening, and you have my contact information, and I think we have time for a couple questions, Joanna?
Yeah, absolutely. So at this time, we did want to open it up to questions. So if you do have a question for Jarrod, please feel free to type it into your questions panel. I do see a few coming in at this time. I'd like to start with our first question for you, Jarrod, where it says, you keep saying that magnetic technology costs less, but by how much?
As far as the standalone encoders, you can probably expect to see a savings on the scale of maybe 20% for a identical optical encoder. For the kit solutions is where you're going to see the biggest savings because you're eliminating that flange, which would probably be the second most expensive, and that's where something on large scale we're seeing a sub $50 device, possibly down in the 20s depending on the simplification of it.
Great. Another question that we got is, how long will it take for magnetic encoders to become dominant in the market? Will optical encoders be around for much longer?
That's a common question. It depends who you ask. I referenced it a little at the end there, and I think the reality is optical encoders really aren't running away yet. There's a strong MRO business for them. People are comfortable with them. Unfortunately, some of the shortcomings of magnetic encoders also spook some people away, if you will. They're slowly coming around. I think they'll be here for a while.
Great. Another question, is one type of encoder better for redundant applications?
That's a great question because people see the optical encoders and you can see how it works. You see how everything fits together, and it gives people some sense of security, if you will. Whereas the magnetic encoder, some people might go and describe it more as smoke and mirrors, if you will, because it is such software based. One of the things though that we can do is actually give you the best of both worlds, and we've had applications where we've combined the optical components and the magnetic encoder all in one unit. So you can address all the different potential shortcomings of both technologies in a unit that is redundant within itself to all of the issues, so the EMC, the shock, the vibration, etc.
Great. Thank you. Another question, are magnetic encoders appropriate for safety-rated applications?
Yes, you'll actually see there's a couple different manufacturers on the market who do offer SIL-rated safety encoders. So they've gone through, I think, SIL level 2 and possibly SIL level 3, depending on if it's single turn or multi-turn. But there's a couple different options out there, and I think you're going to continue to see more over the next few years as more customers are looking for those types of products and the demand increases.
Great. Thank you, Jarrod. At this time, we are getting close to our allotted time limit here, so I want to thank all of the participants today as well as our sponsors, Electromate and Posital-Fraba. And as a reminder, this webinar has been recorded, and an email with the link to the recording will be sent to you within the next 24 hours. If you did submit questions that were not answered during this presentation, they will be answered via email after this webinar concludes. Also, be sure to visit www.motioncontrolonline.org for a list of our upcoming webinars. Thank you and have a great rest of your day.